Alright, I'm going to try here to make moments of inertia. Now, moments of inertia deal with rotations and how bodies rotate. And they are related to, but not the same as centers of mass. What happens for inertia? Let me trying to. There we go. There's my pen tip. Is let's say we have a rotating cylindrical object. So let's try to get my cylinder down here with some central axis. All right, so we have some rotating object. We'll look at this end point of it here as it rotates. Has a contact point with the ground, and it will rotate in this direction. Well, even without a contact point in the ground, but we'll say it's rotating about this central axis L. And as we rotate about it, we can think of little chunks of mass moving about. And so we have little chunks of mass that move through the object. And so we'll have these little chunks of mass, K, some distance from our object. And if it rotates at a regular velocity, so it's going to have some omega, which is the change in theta over the change in time, some angular rotating velocity, then in its center of mass, as it moves forward, traces out a linear speed. Right? Right? The block's little bit has a linear velocity, some v. And so that little v for any part of the block is going to be the change of its position and whatever angle it's at. But since the radius is fixed for the little block, then it's going to be the change in theta, the change in time, or k omega. So we have a velocity component that's r/k omega. Then we have an energy component, which is our little mass component. So we'll look at kinetic energy. Right, 1/2 mv squared, so we have our little mass element moving, and then its velocity component squared. And by substitution, we get 1/2 omega squared, the radial component, times the mass component. And so the kinetic energy itself is going to be the sum of all of our radial component squaring, or I'm sorry, our angular velocity squaring, our radial component squared, and all of our mass elements. So the kinetic energy itself will be the integral of 1/2 omega squared r squared over the infinitesimal mass components, which means we can pull off 1/2 omega squared, and we end up with this r squared dm component. And this part here, because of the analog in kinetic energy in a linear sense is 1/2 mass times velocity squared, and our kinetic energy here in a rotational sense of having this integral is doing the same job as mass, except in a rotational sense. And so, since this in physics is known as the inertial mass, it's the object's inertia is determined by how massive it is. It's the resistance for changing in velocities or directions. Then this is called the moment of inertia for rotations. Or the moment of rotational inertia. And so we call it I. So I is the integral of r squared times the infinitesimal mass element, which means kinetic energy of a rotating body is 1/2 I omega squared. And so there is some parallelism here. And we can talk about moments of inertia as being how hard it is to start something rotating, as it would be the same as talking about mass to be how hard it is to start something in a linear motion. This neatly actually comes into play if I have an object that rolls without slipping on a surface. Then in the center of mass, we'll have a velocity, and this will start rolling at an angular velocity, and so the kinetic energy the object experiences has two components, which means that if my potential energy comes from my height, then different objects' shapes can determine their rotational kinetic energy output. And so different shaped rolling objects will develop different speeds because so much energy is going into the rotation versus what's going into the linear speed. And this is why you can have rolling objects that, even though they have the same potential energy, their motion down a slope will be different because of the energy that needs to go into rotation. Our job is to figure out the moment of inertia for an object. And so what we want to be able to do is we want to look at this idea of r squared dm as something that can be calculable. And what we want to do then is we want to look at, let me get my grid back on here, some mass element and its relationship. We'll look at rotating about the axes right now. I think it would be a good start. Right, rotation about an axis is a trick we've played before and we can continue to play. Put Z up there, Y over here. Let's give ourselves a little mass element. Let's see here. Trying to get my mass element to be mass elementy. Lost my back corner a little bit, but here we have some element of mass, right? And this element of mass has some radial element from the z-axis, that if I drop that straight down, it sticks up a height of z. Has some radial element from the x-axis. Which, looking at it from this side, alright, this comes out. And some radial element from the y-axis. So it itself has a position, x, y, and z. Y and z. And we can look at these lever arms back to the axes and realize that any position back to this axis, however this arm gets here, and this positionally back to the axes, right? These arms kind of have a triangular relationship. Then this arm to the z-axis has a radial value of xyz. The radius it makes x squared plus y squared square rooted. This one from to the x-axis back is y squared z squared square rooted. And this one from the y-axis to whatever this element is going to be x squared plus z squared. And so each axis has a radial component that's kind of defined by the other axes. So if this were rotating or trying to rotate around the x-axis, the lever arm would be the radius defined by the x, or the y squared and the z squared components. So if we want to find the moment of inertia about a given axis, so the I about, let's say, the z-axis, or z or x, we'll do x. Then we'll want to add up all of the mass elements to take care of the dm. And so that means we need to add up all the mass elements of a given density. And so the combination of the density function and the dv function, or the dv components, gives us the infinitesimal of mass. And so if we integrate across the entire solid region made up of little mass elements, we're going to get the dm component, or the mass component. And then now we need to take r squared. Well, if we're going about the x-axis, r squared is y squared plus z squared. If we're going about the y-axis, we're trying to see how we're turning about the y-axis. Then in our mass, again, our density function times the infinitesimal volume function will give us our infinitesimal mass function. And since we're going about the y, our radial component is x squared plus z squared, so we square that, we get these components. And if we're going about the z-axis, we get these. So we can look at the component that resists rotations about axes. Furthermore, if we were going about a line, any line, so I, the moment of inertia about line L, some rotating axis. Remember, rotating axis can be defined by an I, by a line. Then it'll be the radius function to that line times our dv element. So rotations and the ability to rotate get caught up in the ability how the lever arms work, or these little r squared times m. Now that was our three-dimensional ones. The same thing happens in two-dimensional. If we have about the x-axis, then we'll integrate across the region, and we'll do y squared times the density times the differential in the area. And if we go about the region and we're looking at how it rotates across the y-axis, then we'll do x squared times the density element times the differential of the area. About the origin, it will be the radial function, x squared y squared, times the density times the differential of the area. And note, this is the same as ix plus iy. And there's a change of axis theorem that exploits this ability to go about the origin. All right, let's look at how moments of inertia affect different objects. I think it's a fun study in physics. I remember in my Physics 1 class rolling things down slopes and looking at their different moments of inertia. If you look in a Shams or your physics textbook, you'll see that there are different moments of inertia calculated for different solid objects, which tell about them rotating about their rotational shaft. Let's look at finding the rotational moment of inertia for a rectangle. How hard is it to rotate a rectangle, a rectangular solid? And we're going to put the rectangular solid with a constant density, and we're going to put it of A, B, and B. We're going to put the center of the block at the origin. So we'll put the center of the block at the origin. Let's put the center of the block at the origin. We'll give it a width of A, length of B, and a height of C. So let's put our center of our block at the origin. So let's get our region of interest, our region D here, and let's see, we'll put the center of the block at the origin, and it's going to have an x direction length of A. So that means we'll go out to here and back to here. So that means the length in the x direction is a over 2. And then we'll have some height that goes below the origin, up through the origin. I need to get into the middle of the block here. That's in the center of the block there. All the way back. Let's dive it down to here. Huh. Let me. Okay. 2 over, 2 back. That centers it there, centers it there. So I have my y direction, and now I just need my height. So I need to come down this much. Down. Just imagine that I did this okay. We'll put the center at the center will be the origin. I'll redraw my origin from there. Should have drawn my block first and rescoped out my origin. And so if this is 0, this is 0, and where it crosses this axis is 0, then if it has a width of a, an x length of A, a y length of B, and a z length of C. So that puts, with the origin in the middle, then in my positional components, I'll be integrating from halfway, a over 2, negative, to positive a over 2 relative to the origin for my x components. Well, I can turn off my horrible grid. Sorry about that. Trying to get the center on the origin there. And then in my y components will be from negative b over 2 to b over 2. And my z components will be from negative c over 2 to c over 2. And so if I want to find how hard this would be to rotate around the z, what the moment of inertia would be to give it a z rotation, what the resistance to this type of rotation would be, then I'm going to take x squared plus y squared. If I want to find the moment of inertia rotating about the y-axis, going to have the same region, so I'm going to have the same limits of integration. But now I'm rotating about y, the radius to any infinitesimal mass component. And we said these were of constant density. And if I want to find the rotation about the x-axis, and so if we work through the integral, let's do our first integral here. Let's do I of x. So rotating about the x-axis, I will bring my mass element out front. And then we'll do dx. So that's going to be y squared plus z squared And I guess if we really wanted to look at these, right, because of symmetry, the symmetry arguments of the rectangle, I can take this as being 2 of this integral, right? A negative to a positive over an even integral like this, which a constant function would be 2 times. So 0 to b over 2 times 2, 0 to c over 2. So 2, 4, 8. Yeah. I'm going to get 8 times what the integral was. Saves me, puts zeros in my fundamental theorem, which is nice. And so the first integral, 8 delta, 0 to c over 2, 0 to b over 2, and then I'm going to have y squared plus z squared evaluated from, I'll bring in a over 2, right? dy dz. So we'll bring that out. That'll be 4 a delta, 0 to c2, 0 to b2, y squared plus z squared, dy dz. Which means it's going to be y cubed over 3 plus z squared y, evaluated b over 2 to 0. And so that's going to be b cubed over 24 plus z squared b over 2 dz. And a little bit more cleanup here. For a delta, then in our last would be b cubed z over 24 plus z cubed over 6 evaluated from 0 to c over 2. And so for a delta, b cubed c over 48 plus, oh wait, there was a b on there, wasn't there? Yeah, b. Z cubed, 2, 8, so c cubed b over 48. And a little bit of playing here. Each of these have an ABC. A, B, C. 1, 2, 3. Pull out the 48. 4 into 48 is 12. And what is that? B squared plus C squared. Or the radius. And so we have that are delta ABC is the length with height, which is equal to the volume, and the volume times the density is equal to the mass. And so m over 12 b squared plus c squared. So rotating this has a relationship on its size and the proportions to the total mass. If you do this for each of these, because this is symmetrical, then n for IY, it's mathematically symmetrical. We get a squared plus c squared. And for IZ, we get m over 12 a squared plus b squared. All right. A is related to the x, b is to the y, and so you get this, rotation of everything being represented, and your rotations. All right. So that's moments of inertia. They're extremely important things to calculate, and they actually have a parallel in probability functions, where the means and expected values of probability functions deal with what's called the probability density function and their first moments. But I'll do that in my next example.